Machine learning models can look very different on the inside, but most of them follow one simple pattern. Data goes in, the model transforms that data, and a prediction comes out. In this video, we will compare several basic learning models by focusing on architecture rather than code. We will look at linear regression, logistic regression, decision trees, random forests, K means clustering, and a basic neural network. The goal is not to memorize formulas. The goal is to see what kind of structure each model uses to learn from data and why those structures behave differently. Start with the Folkadi. We collect examples, turn them into features, send those features through a model architecture, calculate an output, and compare that output with reality. When the task is supervised learning, the model receives both inputs and correct answers during training. When the task is unsupervised learning, the model only receives the inputs and must discover structure on its own. Linear regression is the simplest place to start. Its architecture is almost just a weighted sum. Each feature gets multiplied by a weight. Then the model adds those weighted features together bias term to produce one contemporaire. That was one now. Every input feature pushes the final prediction up or down in a straight line. If you imagine house price prediction, square footage might add value, age might subtract value, and location quality might add even more. The architecture is shallow, direct, and easy to interpret. But linear regression only works well when the target is continuous and the relationship is roughly linear. It does not naturally create categories like yes or no. Logistic regression keeps almost the same front half. It still computes a weighted sum from the input features. The main architectural difference is the output layer. Instead of leaving the score as any real number, logistic regression passes that score through a sigmoid curve. That sigmoid squeezes the output into a probability between 0 and 1. Now the model can answer questions like, will a customer churn? Will an email be spam? Or will a transaction be fraudulent? So linear regression and logistic regression share a very similar shape. The difference is mostly the interpretation. Instead of one weighted equation, they build a branching structure of questions. At each internal node, the model checks 1-3. Is age greater? Is income below 50,000? Is the pixel darker than this value? Every example travels down one path until it reaches a leaf. That leaf stores the prediction, either a class label or an average numeric value. The strength of the tree architecture is that it naturally handles nonlinear rules. The weakness is that a single tree can become unstable because small data changes may produce a very different set of branches. Random forest keeps the tree idea, but changes the overall architecture from one tree to working together. Eat on the Trondheim. This makes the trees less correlated. During prediction, all trees vote or average their answers. The forest architecture traits interpret into perpleforceability and often delivers stronger performance than a single tree. Notice the pattern here. Linear and logistic regression depend on one global equation. Trees depend on conditional routing. Random forests depend on an ensemble of many routed predictors. Now switch on a supervised model. Random forests depend on an ensemble of many routed predictors. Now switch to an unsupervised model. Every tate is to the coeds to the care. Revolves gmflvikes, they canad. That two-step loop repeats again and again. Assign points. Move centroids. Assign points. Move centroids. The architecture is iterative rather than layered. K means is useful because the visual logic is intuitive. But it assumes clusters are roughly compact and you must decide the number of clusters in advance. Finally, consider a basic neural network. Its architecture is layered. Inputs feed into hidden units. Hidden units feed into deeper hidden units. And the final layer produces the retiction. Inside each night, it's combined away kind, but after that sum, the network applies a nonlinear activation which allows the archetype to tap many transformations instead of one. This is the key leap. A neural network can build intermediate representations. Early layers might detect simple patterns, while later layers combine them into more abstract concepts. Compared with linear regression, the network is far more flexible. Compared with decision trees, the network is network compared with linear regression. Das Messiaen trees are network idea intensive. A dozen in linear in tuning. So when you compare architectures, are three quite to meet agreed. Man just don't declare about. If information flows through one weighted path, you are usually looking at a regression-style model. If information flows through branches, you are looking at a tree-style model. If information flows through repeated centroid updates, you are looking at clustering. If information flows through stacked layers of activations, you are looking at clustering. If information flows through stacked layers of activations, you are looking at a neural network. No single architecture is universally best. Simpler models are easier to explain and debug. More complex architectures can capture richer structure, but they introduce more models of depth. Once you understand the architecture, the training objective and the prediction behavior become much easier to reason about. Click subscribe to follow Explain This Paper for more AI and machine learning breakdowns.